Good morning everyone, I'm O, and today I'll be sharing about embodied carbon calculation, an essential topic for modern civil engineers who aim to design sustainably and responsibly. Our discussion today will connect environmental responsibility with real-world engineering design decisions. By the end of this session, you should be able to 1. Understand the design considerations that integrate environmental responsibility and the professional engineer's role in reducing embodied carbon. 2. Calculate embodied carbon emissions during the product and construction phases of a project. President Emmanuel Macron once said, "By polluting the oceans, not mitigating carbon dioxide emissions and destroying biodiversity, we are killing our planet." Let us face it, there is no planet B. This statement reminds us that civil engineers must design not just for safety and efficiency, but also for sustainability, reducing carbon emissions at every design stage. Let's look at the numbers. Global carbon dioxide emissions reached 41.6 billion tons in 2024, according to the Global Carbon Budget, up from 40.6 billion tons the year before. 2024 is also expected to be the hottest year on record, reaching 1.5 degrees Celsius above pre-industrial levels. Historically, carbon dioxide emissions have increased sixfold since 1950. While the US and Europe dominated emissions in the past, China, the US, and India now contribute more than half of global emissions, with Asia alone producing 6.2 billion tons in 2022. This shows how critical it is for our region to take climate action. These figures are alarming, but they highlight the urgency and opportunity for engineers to make a difference. Now, what exactly is embodied carbon? Embodied carbon refers to the carbon dioxide emissions associated with materials and construction processes throughout a building or infrastructure's lifecycle, from extraction, manufacturing, transport, and construction to maintenance and end-of-life disposal. Reducing embodied carbon is one of the most immediate and impactful ways to achieve building decarbonization. The life cycle of a building involves several carbon-emitting stages: product phase, A1, A3, raw material supply, transport, and manufacturing. Construction phase, A4, A5, transportation to site, installation, and site processes. Use and maintenance phase, B, repair, refurbishment, and energy use. End-of-life phase, C, demolition, waste transport, and disposal. And beyond that, reuse and recycling, D, can further reduce total emissions. Understanding where emissions come from allows us to target reductions effectively. In Malaysia, CIDB Malaysia provides key references. On the left, the compilation of embodied carbon data, over 500 records of carbon data for materials and elements. On the right, the MyCrest tool, Malaysia's carbon reduction and environmental sustainability tool. MyCrest assesses both quantitative carbon emissions and qualitative environmental impacts, supporting low-carbon design decisions. Let's define some important terms. Embodied carbon indicator, the emission value per kilogram of material. Embodied carbon factor or ECF, carbon dioxide emitted per kilogram or ton of material, cradle to gate. Construction and building materials, the raw inputs for building. Building elements, major structural components. Understanding these terms is essential before calculation. CIDB Malaysia has introduced embodied carbon indicator ranges. For construction materials, emissions below 0.5 kilograms carbon dioxide equivalent per kilogram are very low, while above 5 kilograms carbon dioxide equivalent per kilogram are very high. For building elements, emissions below 10 kilograms carbon dioxide equivalent per square meter are very low, while above 350 kilograms carbon dioxide equivalent per square meter are considered very high. These benchmarks help engineers assess where improvements are needed. This slide breaks down the carbon emission calculations for stages A1 to A5, which cover the cradle to construction boundary of a project. A1, A3, material production and manufacturing, A4, transportation to site, A5, construction and waste. To estimate embodied carbon emissions, we follow a simple yet systematic procedure. 1. Identify material quantities. 2. Obtain embodied carbon factor ECF values. 3. Multiply. Embodied carbon equals quantity times carbon factor. This method can be done using a spreadsheet, or more efficiently, with online calculators provided by credible organizations or national tools like MyCrest. Let's summarize the calculation method with a simple example focused on the production stage, A1, A3. Carbon emission from the production can be calculated as quantity of material multiply specific ECF. For example, suppose we are using 2,300 kilograms of concrete, grade 30. Refer Appendix 1. ECF equals 0.13 kilograms carbon dioxide equivalent per kilogram. Right pointing arrow 299 kilograms carbon dioxide equivalent. Carbon emission from the transportation of construction material or specimens can be calculated as distance multiply specific ECF based on type of vehicle and fuel used. For instance, 500 kilometers by heavy truck, greater than 20 ton, ECF equals 2.7 times 0.336 kilograms carbon dioxide equivalent per kilometer. Right pointing arrow 454 kilograms carbon dioxide equivalent. If there are construction machinery at site, the carbon emission can be calculated as quantity diesel used multiply specific ECF. For instance, 100-liter diesel, ECF equals 2.7 kilograms carbon dioxide equivalent, liter. Right pointing arrow 270 kilograms carbon dioxide equivalent. For exporting the waste to landfill, carbon emission can be calculated as quantity waste multiply specific ECF and distance multiply quantity transported multiply specific ECF. For example, 1 ton metal waste plus transport right pointing arrow approximately equals 474 kilograms carbon dioxide equivalent. Remember that 1 ton equals 1,000 kilogram. You can also refer to my CREST calculator in the calculation and you can find the specific ECF in the references and appendix at the end of the video. Let's apply this to a case study. There are a few limitations in the case study. A 4-story apartment at Section 7, Shah Alam, is to be constructed, with a built-up area of 2,800 square meters. We'll estimate embodied carbon from stages A1 A5 using data for production, transport, machinery, and waste. To calculate the carbon emission for the case study production stage, first, list the material quantities such as concrete, reinforcement, plywood, bricks, metal decking, and finishes. Then, determine the ECF for each material. This followed with multiplying each material's quantity by its ECF. Lastly, sum all emissions for total embodied carbon. And the detailed calculation for transportation. Machinery. And waste. From the calculations, total embodied carbon, A1A5, 405 tons carbon dioxide equivalent. Or equivalent to 145 kilograms carbon dioxide equivalent per square meter. This revealed that the construction project in the case study is categorized as medium-level emission. This figure provides a baseline for design improvement and comparison with low-carbon benchmarks. Finally, here are several strategies to reduce embodied carbon: carbon sequestration through tree planting and green roofs, water conservation, rainwater harvesting, greywater recycling, energy efficiency, insulation, efficient lighting, motion sensors, renewable energy, solar PV systems, construction waste management and use of biodiesel or gas-powered generators. I recommend watching the UN Environment Programme's video on global carbon trends. It provides strong motivation for sustainable action. This video serves as a reminder to engineering students on their responsibility and contribution to the sustainable design and practices. To end, remember this quote: "The way to get started is to quit talking and begin doing." Walt Disney, Sustainable Design for Better Life. The rest of the video shows the important references and appendices in the calculation. Embodied carbon is not just an environmental statistic, it's a call to action for engineers. Every material choice, every design decision, and every phase of construction presents an opportunity to reduce our carbon footprint. Let's design smarter, build cleaner, and engineer a better future.